Hello and welcome to Empowered Learning. This video will be about definite integrals. So to start off, we're just going to read the theorem for definite integrals, make the interpretation of what that's really trying to say, and then from there, of course, we'll see some basic rules or some basic facts after defining what a definite integral is, and then we'll do some practice problems. So our theorem says, let f be a continuous function on a closed interval of x values from a to b. If we have that condition, then the Riemann sums for the function f on this closed interval approach a real number limit I as n approaches infinity. Now, in regular people's terms, what this actually means is this. If we have a function that does not have any breaks, holes, gaps, vertical asymptotes, jump discontinuities, anything like that over some closed interval, then what we're saying is when we say the Riemann sums, we're saying that the sum of the finite areas under the curve, if we took our function here, and let me go ahead and draw something right quick. So let's say if we had a function that looked like this from A to B, and we're looking at the area under here. So if we were to slice this area under here with into a bunch of tiny rectangles. So let's say we come here, we slice it up into these tiny rectangles here. If we added up all the areas of these really small rectangles here, that would be what's called the Riemann sum. So here going from A to B, and I think I messed up my B there, so I'm just going to try to draw it like that, or maybe I'll just erase it. That's probably better. So coming back to where we were here, if we know that we have some function that doesn't have any breaks, holes, gaps, jump discontinuities, or anything like that, then the sum of all these little rectangles here that we can use to approximate the area for this function from where x equals a to x equals b will approach some real number I here. And what we're saying there is we know that each of these rectangles will have a width of delta x and a height of f of x, depending upon what the value x is. And as this delta x gets closer and closer to 0, theoretically speaking, and the smallest theoretical incremental change in the x values, we actually call that dx, or the differential of x. Then as it approaches that, the behavior of the sum of these areas of rectangles tend to go towards some real number I. And of course, we're trying to describe the behavior here, and that's why the word limit is there. Okay, so in short, the area under the curve of this function from as defined in between these two x values will approach some real number. That's basically what we're saying if we have this condition. And this A and this B is what's called the limits of integration, meaning how are we trying to box in this particular area here. Of course, the integrand, as we call it, is the function f of x. And so that's all the definite integral is trying to say. Now, whenever we looked at this earlier, this is what's called an indefinite integral. And when you do this, you know that the outcome is going to be what's called the most general antiderivative plus some constant c. And of course, the constant c is there because there is a bunch of functions, big f of x, where the derivative of big f of x is equal to little f of x. And so you don't know which one you're talking about, so you have to basically add a constant to that to say that, hey, these family of curves actually satisfies getting the antiderivative for this. Whereas here, we have a specific antiderivative that's going to work for it. And of course, we know that because the limits of integration is going to sort of force us to be able to find out which particular one are we talking about, okay? All right, so let's move on here. So whenever we're talking about area under the curve, one of the interpretations that we need to know is that whenever we're talking about area under the curve where the area is above the x-axis and with the x-axis, so everything that is above the x-axis to the x-axis, any areas that are enclosed by the function and the x-axis is going to be positive, and any areas that are enclosed by the x-axis and the function, if it's below the x-axis, is considered to be negative. And so that's what this particular slide is trying to communicate. Now, if we look here as an example, we'll see that if the area of A is 3.5 and the area of B is 12, then how we would actually interpret this is the area under the curve of the function f of x from A to B would actually be split into two different areas. From A to C rather. It will be split from A to B, and then it will be split from B to C. And then of course the area under the curve from A to C is just going to be the sum of these, where we know that this area is negative here and this one is positive. All right, so where are we going with all of this? So if you've watched my previous videos, then you've seen how we've looked at the area under the curve and tried to estimate that by using rectangles, and we come up with these Raman sums, and you can see with some of the previous examples that we've had from those videos that that can be a long and tedious process, especially when we're trying to take the limit of the Raman sums and rewrite everything. But of course, just like how we do with derivatives, of course with derivatives you start off by taking the limit of the difference quotient, and of course you want to find a better, faster way to do that. So we're going to do the same thing with integrals. And so in doing that, we want to find a better, faster way to do it. And so part of what we need to do before we can get to that point is to study what some of the basic properties of integrals are. Now, in general, in your study in calculus, no matter who you're taking or where you're studying, some of the basic things that you'll be doing is finding out what the basic properties of integrals are. You'll be finding you some shortcut formulas, just like how we had the differentiation rules for derivatives. You also have some integration rules for integrals, and then you'll see some specialized integration techniques to help you evaluate more complex integrals. And so after learning how to do the basics, which is some of the easier functions where you can kind of see what's going on by looking at the area under the curve of it, and it looks like known shapes that you know areas for. Of course, after that, we do some more basic integration. And then later on, it comes to where you're doing substitution. And then after that, integration by parts, that whole thing. So those are some of the techniques that I'm talking about. This video will only cover just basic integration and the ones where you can interpret or calculate the area under the curve by interpreting the area as a known area, geometric shape, whatnot. So other videos that I have will go over substitution, integration by parts, that whole thing. So look out for those. Of course, the fourth toolbox here that we also learn about is the fundamental theorem of calculus. And so we will talk about that and study it in this particular video. And this tool is very important because the fundamental theorem of calculus bridges what we do for differentiation over with integration. And so in every subject in math, there is a fundamental theorem that sort of brings everything together. And for calculus, it is the fundamental theorem of calculus. And we'll see that it has two parts to it. And with those two things, it allows us to be able to go back and forth from differentiation calculus to integral calculus and to be able to interpret those and relate those two together in their own geometric interpretations. So again, right now we'll be focusing on toolbox number 1, but in other videos we'll do some of the more specialized things and the fundamental theorem of calculus. We'll also take a basic look at that in this video. Now let's look at some of those basic facts or basic properties. So we see here that the first property we're saying, and remember, every time we say the integral of something, we're talking about the area under the curve of this function here. So the order of integration, the limits of integration, this number has to be smaller than or equal to this number. So the assumption is that when we do all these rules, A is less than or equal to B. And in the case where we have B down here and A up here, it's like we're looking at the area backwards, if that makes sense. And so what we're told to do is to basically flip everything around, but we're going to have to multiply everything by -1. So this is the interpretation for that. So this, in another way, this is like reading the area under the curve going from right to left instead of from left to right. And since everything is reversed, we know that, or the opposite, looking at things as opposites, we know that we would have to make it the negative of what it was, since we're looking at area as being above the x-axis and below the x-axis. Okay? So rule number 2 gets into saying, hey, if I have a function and the limits of integration are the same, then technically what that looks like is this. So a function that has technically no width, so therefore you can't have any area if you have no width. So that's why for here, f of x, if you take the integral of that and limits of integration are the same, it'll always be 0. Constant multiple rule just basically says, just like how we do with derivatives, if you're taking the integral of a multiple of some function, you can just pull the constant out and take the integral of the base function. The sum and difference properties, just like with derivatives, if we're going to take the integral of the sum or difference of two functions, that's just like taking the integral of each and then just adding or subtracting those answers together. The additivity property basically says that I can take a function, kind of like how we've seen in my example here, previous to this. We can take a function and actually split it up into, well, not function. We can take the definite integral here and split it up into 2 separate definite integrals. And so in the example that we had seen, and I'll go ahead and go back to that now so that this will all make sense. You see how we had a portion of the area that was below the x-axis and a portion that was above. So this would be a good way to use that property in trying to split up, hey, well, what is going to be the portion of the area under the curve that is below the x-axis, and what is going to be the portion of the area that's above? And so we know that the sum of this and this would end up being this definite integral here. So that is how the additivity property is used. All right, so number 6 is the max-min inequality property. And what this property basically says is that if we wanted to find the area under the curve of some function, then we can estimate it to be in between what the minimum value of that function is times the difference in between x equals b and x equals a. And it'll also be in between, on the high end, the maximum value for that function times b minus a again. And so what we mean by the maximum of the function is how high it actually goes in between when x is equal to a and x is equal to b. And same thing for the minimum. So to get a better idea of this, we'll actually look on the next page here to kind of see a drawing of the two. And so I'll go ahead and go there now. And so we can see here what we're talking about. So we see that in between x equals a and b, that the max value of the function is at this particular point, and the minimum value of the function is here. And all we're saying is that the area under the curve of the actual function f of x is going to be at least whatever the area is of this rectangle, and at most here, depending on what the function is. Now, of course, the actual interpretation of this is just the actual area under the curve here, of course, going all the way down, will be somewhere in between this rectangle made by the minimum value of f and b minus a and the maximum value of the function f and b minus a within this closed interval. Okay. Now, since we're here, let's go ahead and look at the domination property as well. And this property is basically saying that if we know that some function f of x has y coordinates that are above or equal to another function g of x for all values of x in between x equals a and x equals b, then that means that the area under the curve of the function who has higher y values is going to be larger than or equal to the area under the curve of the function that is below. And so that's pretty much what that says. And so you can see I've described some of the other properties before, and you can see their corresponding graphical interpretations of this. And these are some of the basic things that we just have to keep in mind whenever we are evaluating intervals. So let's go ahead and move forward. So on this page, I just made a copy of a basic integral table, and as we work some of these problems, we'll refer back to these just to make sure that you are aware of them. You may want to pause the video right now and either write these down or look into your textbook that you're looking at, or just a particular website that may have these, and make sure that you have these handy. Of course, you'll need to memorize these, but of course, the best way to memorize them is just to practice a lot. So I would start off just basically doing a lot of problems and having them near you. And as the more and more problems you do, the more and more you'll see that you will recognize what these integrals are, and you'll get to a point where you won't need the tables anymore. Okay. And I'll just go ahead and scroll down here. Make sure you can get some of these others. So you can just pause the video here for a second and get them. Okay, I'll go ahead and move on now. All right, so here's our first problem here. And what we want to do is evaluate the following integrals by interpreting each in terms of its known area. Okay, so here we're going to be looking at this problem from a conceptual point of view. And the hint that's given here is that this function, square root of 4 minus x squared, if we were to actually square both sides and rework everything to where we just have 4 by itself, we'll see that it is this equation here. And what we know is that's actually an equation of a circle. Okay. And if we wrote everything out explicitly, it would look like this, where this is a circle and the radius of that circle is 2. So in knowing that, what we want to find out is what is going to be the area under the curve of this circle from 0 to 2. So that's basically from here to here. So we're talking about all this area that is inside here, or basically 1/4 of the circle. So if we looked at that, we know that the area for a circle in general is just pi r squared. And so in this case, since r is equal to 2, the area of the entire circle here would end up being pi 2 squared. Okay? But since we only have 1/4 of the circle, the actual answer to this would actually be just pi 2 squared divided by 4. Okay? Because of course we just want 1/4 of the entire area. And so by doing that, we see that the numerator is just 4 pi over 4. And so this would just end up being pi square units. Okay? And that pretty much is it for that problem. So we interpreted it correctly. And of course, we calculated the area and just interpreted it as, hey, we want 1/4 of the area of a circle. And we pretty much plugged in everything from there. So let's move on to the next problem. So we see that this problem is already worked out for us, but we also have a nice graph here as well. And we see that we want to find the area under the curve of the line x minus 3 from -1 to 6. And you see we've drawn a line here from x equals -1 to 6 to get that line segment. And of course, we have two different areas that we are considering. And one is the area under the curve from -1 to 3. We know that because the function y equals x minus 3 has an x-intercept at x equals 3 here. So that's where the area starts to change from being negative to positive. So we need to look at the area A1, and from 3 to 6, we need to look at the area A2. And so for this triangle here, we see that the width, or the base of this triangle, is 4 units. And the height of it, if we keep going down, is going to be 1, 2, 3, 4 units as well. So that's how here for the area A1, we just get 1/2 4 times 4, because we know the area of right triangle is 1/2 base times height. And so we end up getting 8 square units there. Now for the area A2, we see that the length from here to here is 3. And of course the height, that's going to be 3 as well. So 1/2, 3 times 3 gives us 9 halves, or 4.5 units. That should be square units as well. And so now all we do is just subtract these two, because we know since A1 is under the x-axis, the area is enclosed in between the function and the it's enclosed in between the function below the x-axis and the x-axis. Then we have to make that negative. And so that's why when we have this, you start off by knowing that the area from -1 to 3 is negative, and the area from 3 to 6 is positive. And of course, it's expressed this way. You plug in the numbers that we calculated here, and we'll see that the net area is going to be 3.5 square units, but it's going to be below the x-axis and not above. So that's what that negative means there. All right, let's move on to the next example. All right, so now what we want to do is suppose that we have some function x plus 1. Of course, it's a line. And we want to look at that function from when x is -1 to 2. And we want to determine, is the integral of the function f of x from x equals 1 to 2, is that non-negative or not? Or put another way, is the area under the curve, the net area, strictly above the x-axis? Okay, or is it going to be positive? Let's put it that way. So we want to show this by sketching a graph first, and then interpret what the area is. And then after that, we want to show the answer by calculating the definite integral by computing the known area under the curve. Okay. So let's go ahead and sketch a graph of x plus 1 from -1 to 2 here. So got this. We'll just do from -1 to 2. And we know that whenever we plug in a -1 into here, -1 plus 1 is 0. So here, what we would have, I'll just draw it first and then bring it down. So that would be there. And so now when we plug in a 2, that will give us 2 plus 1 is 3. So we'll come here, the value of 3, that would be like that. And so now this is going to be a line, goes through there. That didn't quite come out well. Let's try that again. All right, so we'll come here, go through there like that. And we know that this is going to be a y-intercept at 1. And so here what we're looking at is this area. And of course we see that this is a triangle and the area is strictly above the x-axis. So we know from that this area is going to be non-negative, okay? So we know from here, non-negative just means that it's going to be greater than or equal to 0. Now, when we actually interpret this, we are interpreting it, let me make sure that I put this, we are interpreting it as, of course, this, which will also be 1/2 the base, which in this case is going to be 3, and the height, which in this case is also going to be 3. So this is going to be 9/2 square units, so 4.5 square units. Okay, and so that's how we do that. Now, of course, there is a way to do these by using integration rules or taking the antiderivative of that function, but we're not at that point yet. We're going to get there soon, though. All right, so next what we want to do is consider 3 functions here. One is going to be f of x, which is a horizontal line, y equals 5. Another one is going to be g of x, which is another horizontal line, y equals 2. And then we have a linear function, 5x plus 5. And what we want to do is draw the graphs of these functions so that we can show that the area under the curve from 1 to 2 of the function h of x is actually going to be in between 2 square units and 5 square units. Okay, and so what this is actually trying to do is this problem is trying to illustrate the min-max inequality rule. Okay, so I'm going to go ahead and draw this, and let's see. Yeah, I think I'm gonna pause for a second here and actually draw everything so I can do it in different colors, and then from there we'll kind of see what we're talking about. All right, so we're finished drawing f of x equals 5 and g of x equals 2 on the closed interval from 1 to 2. And if you notice, I'll also change my function h of x here. I realized what I had wasn't necessarily going to work, but this 3x minus 1, one will actually show you what it is, and I'm trying to get across in this example. So go ahead and change it if you're following along. So what we want to do now is draw the function h of x on here and kind of see how it fits in between these two areas. So in red, I have the total area of the minimum value of what our function will be from x equals 1 to x equals 2. And I have the area in blue as its height is going to be the maximum value for the function 3x minus 1 in between 1 and 2. All right, so if we go ahead and draw the graph of 3x minus 1, we know that we're going to have y-intercept at y equals -1. And then when we plug in 1 here, we'll get a corresponding y value of 2, which will be right here. So I'll just take that point and we'll slide it in there. And then we also have, when we plug in 2, we get 5. So we'll take this point and we'll slide it right on top of there. And then of course from there, of course I know this isn't drawn to scale, but I'm going to kind of try to draw the line so it'll look something like that. And of course, the actual area under the curve will be all of, oops, didn't mean to do that, will actually be everything that's under that particular function there. So I'll try to find me, so it'll be more so like this. Okay. And so by showing that, we see that the area under the curve from 1 to 2 of f of x is just going to be, and I need to get the notation right here. Now that's just going to be the height of f of x, which is 5, times the difference in between 2 and 1, and that's just going to be 5. And going from 1 to 2 of g of x, same thing, that's just going to be 2 times the difference, because of course though that is what the length and width of the rectangles are. And of course, if we take the area under the curve of h of x, we see that that's going to model, and I'll actually do this another way here so it'll look something more like this, where we know this area is 2 square units, and we just need to figure out what the area of the triangle is here. And so, of course, the area of this triangle will be 1/2 the base times the height. And of course, the base is length's just going to be 1, and the height is going to be the difference in between 2 and 5, which is 3. So that would be 3/2. So basically, we would have 1/2 times 3, 1 times 3, which is 1.5 square units. And of course, that'll be added on to the 2 square units here. So I forgot to do that. So let me go ahead and get rid of this and try to account for that. So this will be, we'll call this area 1, and we'll call that area 2. So this will be area 1 plus area 2. And this will be 2 square units plus 1/2 times 1 times 3. And of course, all that will give us just 1.5 square units. So this gives us 3.5 square units. All right, so let's move on to the next example. All right, so again, we're going to use the min-max inequality property to be able to estimate what the area under the curve of this function will actually be, of course, square root of x from 1 to 4. Well, one thing we know already is that square root of x, this function in general looks like this. And of course, if we're going from 1 to 4, kind of have this going on here. So this will be our min value. This will be our max value. And if we're trying to find the area under the curve between here and here, we're basically talking about this area there. Now, we also know that in that, we know that the m right here stands for the minimum value of the function in between 1 to 4, and we know that the big M stands for the maximum value. And since square root of x is a monotonic function that is increasing, it's monotonically increasing, then of course the minimum value is just going to be 1, the maximum value is just going to be 2. So here we could interpret M as being the area under the curve from 1 to 4 of, let's see, the function 1 dx. Okay, or we can just put it another way. This is just going to mean the minimum value of f from 1 to 4. Okay, and this will just end up equaling that minimum value times the difference in between 1 and 4, so that will end up being 3. Big M is the maximum, same thing. We know that the maximum value is going to be 2, and that's going to be the same as max value of f from 1 to 4, and that will be 2 times the difference in between 4 and 1, which will be 6. And so we'll see that the area under the curve of the square root function is going to be somewhere in between 3 and 6 square units. Okay? And of course, the tighter we make that closed interval, of course, the area would be different. We also know that the more Raymond sums rectangles that we stuff in between from 1 to 4, the more accurate we'll get. But based upon our limits of integration here and what we're being asked, we just know it's going to be somewhere between 3 and 6 square units. All right, so in our next example, we see that this one's already worked out, but it's showing some of the similar things I've been doing before with the min-max inequality property. We've taken this cubic function and we've drawn it for values of x in between 0 and 2. And we see that from the graph that f of 0 is equal to 3 and that f of 2 is equal to 5. And that A is going to be the area under the curve with respect to the x-axis there, okay? So we know from the min-max inequality property, we know that we can estimate this in between 2 and 10 because, of course, here at f equals 1, you have the lowest value, which is 1 of this function, and at x equals 2, the function has the highest value or the maximum value within that closed interval of 5. So if we look here, we know that all this area here is going to be a minimum, and that's going to be the 2 square units. And of course, the maximum here would be this whole rectangle here, and that would be 10 square units. And of course, the actual value of our function, which is in black there, is somewhere in between there. All right, so next what we want to do is express the following limits as a definite integral on a given interval. And so if you've watched the videos on the Riemann sums and estimating the area under the curve using Riemann sums, um, you'll know that this combination here, the limit of an infinite sum, the way that we rewrite that as is an infinite sum from A to B. So that's actually when we say the integral of something, that is actually what we're doing here. This delta x here, that is the width of each Riemann sum rectangle. And of course, theoretically speaking, if we were to stuff an infinite amount of rectangles in there, then the width would no longer be delta x, it would be the differential dx. Okay? And so because of that, of course, we know that the limit of the infinite sum here would turn into just this s, and of course this is the limit of the limits of integration here, or as it is interpreted here, we're looking at the area under the curve of this function enclosed by these x values, and so that's what we put here. The cosine x of I just says, hey, it just depends upon what rectangle that we're on to figure out that particular area, but in general this is just x. And so if you wanted to interpret this, this would just be the integral of cosine x divided by x dx evaluated from pi to 2 pi. Okay. So now that we see that, we can go here and actually interpret what this integral would be. So of course, again, keeping in mind that all this just means infinite sum. This part here tells you from 2 to 7. And we know that this part here is going to be the infinitesimal difference in between the x values, which is dx. So this will be the integral from 2 to 7 of 5x cubed minus 4x dx. And that's what that interpretation would be. All right, moving forward here, we want to evaluate the integral of sine squared x times cosine to the fourth x, where the limits of integration are the same. And if you remember, since the limit of integration are the same, doesn't matter what it is, we know that the area under the curve there is nothing. So the answer to that would be 0. And for this problem, we see that if we have some integral from 0 to 1 of some function 3x times square root of x squared plus 4 dx is equal to this irrational value, then we want to know what is this particular integral going to be. And assuming that we let w equal x here, then of course this looks exactly the same except for the limits of integration. And so we know that if we were going to evaluate this, we would have to switch this around, but it would have to be negative. So if we did this, this is what it would have to look like. So we have to go make that negative of that, go from 0 to 1. And so now this would just be negative of what we have seen earlier here, minus 8. And so that would just be positive 8 minus 5 square root of 5. All right, so we're finally at the point where we need to talk about the fundamental theorem of calculus. And